Good evening, everyone, and welcome to our today's seminar. It's my pleasure to introduce our speaker, Dr. Edoardo Ponti, who is a lecturer in natural language processing at the University of Edinburgh and an affiliated lecturer at the University of Cambridge, and also a visiting professor at NVIDIA. So his research explores some of the most fundamental challenges in NLP field, including efficient memory and tokenization, modular deep learning, and computational typology. His work has been widely recognized, earning him a Google Research Faculty Award, Best Paper Awards in multiple different conferences, and he's also a key figure in computational typology and co-founder and the board member of a special ACL special interest group. So on a personal note, I'm especially happy to welcome him today because one of my former master's students, Batur, is now doing a PhD with him, and it's always exciting to see these kind of academic connections grow. And I look forward to hear more about your work. Thank you again, Edoardo, and the stage is yours.
Thank you so much, Aykut, for the very kind of introduction. And yeah, obviously, it's also interesting from my perspective to see Batur's former lab, to see, the kind of people he's been interacting with. So it's really a pleasure to be here. Thanks again for the invite. As you mentioned, the focus of today's talk is adaptive tokenization and memory in current foundation models. So let's start from the beginning. So we have nowadays plenty of architectures. They range from different scales to different kind of blocks or layers. Obviously, the most popular ones, at least for language models, are transformers and state space models. Both of these obviously are high-level families that encompass a wide range of different variations. But what really matters is that most of them, if not all of them, make very similar assumptions that I would argue are highly suboptimal. So the main assumption they're making is that the granularity at which information is processed is determined by the tokenizer that maps raw strings of data into sequences of tokens. And once that sequence length is given by the tokenizer, that remains identical across all the layers. That is kind of a strong assumption, and we'll see how it is detrimental to the efficiency of the model. The other important point is that because of this, also the memory grows linearly in transformers. I'm using here a very general term, which is memory, but in these different families of models, you would think of it as corresponding to the key value cache in transformers, which is basically the key and value representations that are appended to a cache as a way to avoid recomputing them during generation. And you would think of this memory as the state space for state space models, which is basically the state that is continuously updated along the sequence. So the memory currently is either growing linearly, which obviously is not ideal because it means that with long sequences we might end up running out of memory, considering that both the KV cache and the parameters have to be stored on the VRAM when we use accelerators like GPUs. Or on the other side, for state space models, this memory might run out of capacity because it has a constant size. So it means that it can include only a certain amount of information before running out of internal space. So how do we avoid these two kinds of problems? So avoid running out of VRAM and running out of capacity of the memory to represent information contained in the sequence. Obviously, this has important ramifications. So I said that this granularity defined by tokenization and the inefficient memories are obviously inefficient by definition. Here I'm plotting on the left two kind of scenarios on whether you use current models which are shown in red, plotting both the amount of energy they require and the amount of CO2 they emit, so their environmental impact, and how that changes between 2022 and 2026 in terms of European usage. And obviously, you would find very similar patterns if you display the same for other continents or countries. So we have a responsibility to make models more efficient, both to democratize AI, to make these models accessible to a larger amount of the population and researchers, on the one hand. On the other, we have a responsibility to make sure that the environmental impact of these models does not result in, you know, CO2 emissions that are, as you know, highly damaging. However, in addition to efficiency, on the right, you also have another kind of advantage that relates more with the performance or accuracy of these models. More specifically, if you have a way to be efficient about the granularity of the internal representations or the dimensionality of your memory, then you can operate on much longer sequences in input and output while having shortened sequences inside. And by longer sequences, I mean either longer inputs, which means that you can now process long context text and other modalities that are by nature long context, like genome, for instance. In terms of long output, nowadays sequences that are long emerge naturally in the context of test time scaling. So it is a case where you sample multiple sequences in parallel, and each of them is a chain of reasoning. So we want a way to make sure that on the one hand, we can explore more sequences at a time, so to have more branches in our search for chain of thought, and on the other hand, explore longer sequences as it might be required for certain problems. So if we had an efficient way to modulate the granularity of representations within foundation models, we would get the best of both worlds, which is higher efficiency but also longer horizons, which applies to both longer contexts and longer chains of reasoning. More broadly, I think this kind of research is a direct continuation of the better lesson, which is a concept that Sutton introduced in 2019, and at its core says that in practice, increases in efficiency in search, for instance, or architectures, directly result in better models because it opens up new possibilities for existing models, so it does not just translate into more efficient models but also better performing ones. So for instance, two very famous examples are a invention of backpropagation, at least in its modern form, which is efficient gradient estimation by Seppelin and Ma, which opened the door to deep multi-layer perceptions. So this change in algorithms that was more efficient resulted in the possibility to have more expressive models. The second example is transformers from Vaswani and others from Google in 2017, which can be conceived as a way to make models more efficient as they allow for parallel training, which in turn resulted in the era we live in, which is the era of large language models and foundation models. So what I'm trying to argue here is that looking for higher efficiency is a way to open up new possibilities also in terms of abilities and emergent abilities of the models. So the question I'm trying to answer in a nutshell is, can we doubt the granularity of memory and tokenization in such a way that we achieve conditional computation? So we allocate an amount of compute for any given task that is proportional to the complexity of a problem, and doing so, we both make models less polluting, more democratic, and on the other hand, capable of handling longer context and longer chains of reasoning. So this talk is structured as follows to answer this question. First part has to do with tokenization. I will introduce two main techniques. One is zero-shot tokenizer transfer, the other is dynamic token pooling. They will increase the efficiency of the models in two ways, respectively. Zero-shot tokenizer transfer leads to more efficient encoding, which in turn opens up the possibility to do model merging and mixing with models with different tokenizers. Dynamic token pooling instead is a way to speed up both training and inference by reducing the quadratic complexity of transformers, which gives you both better models in terms of language modeling and downstream tasks, but also is suitable to model information at the byte level instead of using tokenizers. So it's a way for models to break free into tokenizers, and this in turn means that we can operate on multimodal data in a raw form, which gives us a sort of omnimodal model as a result. Second part of the talk has to do with memory, specifically dynamic memory compression, which is a technique we introduced to increase the throughput during generation and decrease the latency, but also has the advantage of handling long sequence tasks that would be impossible if we used vanilla transformers. So let's start from part one, tokenizers. As we said, currently models are bound to fixed tokenizers. You can't arbitrarily change the vocabulary of a model or the way a raw string is mapped into tokens without retraining the model, on the one hand. On the other, as we said, once you have that tokenizer, that automatically determines the granularity of the sequence that encodes the information about your data. So there are a lot of problems that can emerge from these two assumptions. One is, obviously there could be a mismatch between the data mixtures the tokenizer was trained on and the language model was trained on, which means that the encoding is suboptimal. And this is very, very often the case, unfortunately. So this is one disadvantage. Another one is that especially if the domain or language you're encoding is low frequency or low resource, then it is encoded in a very inefficient way. Think about languages that don't use a Latin script, or languages that are extremely low resource, like some Indian languages that, however, are spoken by a very large number of people. Well, for these languages, the models can be even 5 or 6 times less efficient compared to English. So obviously this is something we want to overcome. And this applies not just to natural languages, but to artificial languages too, meaning programming languages like Python or Java. Another issue here with fixed tokenizers is that they're hard to mix and merge when we deal with models with different tokenization. So if we want to interpolate the probabilities given by different models, but we operate in different vocabulary spaces, obviously that's not possible. We have to match the vocabulary space before being capable of doing that. In addition, tokenizers in generally expose models to a lot of vulnerabilities. Some of these have to do with the fact that from the tokenizer you can infer the data mixture that was used for training the model. So you can attack and discover what kind of data was used for training. The other kind of attack has to do with glitch tokens, which is basically a way to prompt models to behave erratically or unpredictably just by prompting them with certain classes of symbols or tokens that are tokenizer dependent. So if we could get rid of tokenizers, or at least be able to change the tokenizer arbitrarily, we would solve all these problems simultaneously. And just to give you a bit more insight into this kind of issues you have with tokenizers, well, you can see some examples here on the right where, for instance, vowelization or its absence, say in the Arabic script, results in very different tokenizations even if the word is exactly the same. You also have cases where misspellings result in very different tokenizations, even if obviously you might want to reuse the same encoding or symbol because it is clearly mapped to the orthographic form of that word. Similarly for, similar characters in terms of how they appear, or the fact in some scripts like Hangul in Korean, you might have some shared character components that are not usually parsed correctly by tokenizers. These are like just a few examples taken from this very nice paper from Celeste and others from 2021 that show that the encoding provided by tokenizers is suboptimal and also inefficient. So how do we propose to solve that? We first propose a new problem, which we call zero-shot tokenizer transfer. The problem is as follows. Given an LLM with a given tokenizer it was trained with, can be arbitrarily swapped with a new one on the fly, where on the fly I mean with minimal overhead and without new examples, without degrading performance, so retaining the original model capabilities. This builds on previous work that was centered on adding new tokens, for instance, integrating new scripts, because in this specific setting where you do zero-shot tokenizer transfer, it's not just the case that you're adding more information in terms of new tokens, but you also have to update the representation of tokens that already exist, because their meaning might change based on how the rest of the vocabulary is formed. And once we introduce this problem, we also propose a solution. I'm not sure it is the optimal solution, but it is one in that direction, which is learning a hypernetwork that, provided with both the old tokenizer the LLM was trained with and the new one you want to swap in, predicts the corresponding embeddings for the new tokenizer. So it looks something like the picture on the bottom of the slide, which is I give you some text. The text is passed to a tokenizer. The tokenizer is passed to a hypernetwork that predicts the input and output embeddings that correspond to that tokenizer and vocabulary. And then you can train the hypernetwork based on cross entropy with the output text. So how do we implement this process more specifically? Consider this example where you have a vocabulary coming from the original model. So let's say that you have a sentence like the flower beds among something else. So the process looks like this. You start from those which are shown in blue. You first decompose them according to the original tokenizer, T, that returns you the first block of tokens you see in the center red box. You embed those with the original embeddings of the original LLM and then pass that information to your hypernet. The hypernet takes that information for each token and returns the embeddings it predicts under the new tokenizer, assuming the new tokenizer just tokenizes the words one-to-one. So given the old tokenizer again and the new tokenizer, what we want is the hypernetwork to return the embeddings corresponding to the vocabulary of the new tokenizer. And I won't go through the exact details of the algorithm, but there are two key components I want to highlight. One is that we want to have diversity. And this is because we want to expose the hypernetwork to as many different possible tokenizers as possible during training, so that when they're presented with a new tokenizer at test time, it is hopefully close to one of the observed ones during training. To get that, we need diversity, both in terms of vocabulary and in terms of frequencies assigned to those vocabularies. I don't know if you're familiar with tokenizers of the family of unigrams, but unigrams rely on these two main sources of information. Vocabulary, so which are the tokens available here, and frequencies, what is the frequency assigned to each of these symbols. And given these two sources of information, they return you the tokenization for a text string. So we want diversity in both these aspects. To have diversity in vocabulary, instead of passing the entirety of our data to the tokenizer, we just pass a rolling queue of texts. So basically different subsets of examples to the tokenizer, any training iteration. And then we want diversity in terms of frequency. So we add some noise to change the empirical distribution of frequencies of each of these vocabulary items into a smoothed or noised one. So having this diversity in vocabularies and frequencies basically has the effect to expose the hypernetwork to many diverse tokenizers, so that it is then easy to generalize zero shot to entirely different ones. In terms of results, we evaluated our model in many setups, but I will just highlight a couple of them here. One is evaluating them on encoder architectures, so XLMR, which are multilingual, on downstream tasks like natural language inference, which is basically the tasks of given a premise and a hypothesis, telling whether the two are in contradiction, they are entailed, or they are neutral, so they are not connected to each other. So for this downstream task, we evaluate the original model and many different previously proposed strategies or strategies that we adapted for this new problem. And it turns out that, in fact, we can substantially reduce the sequence length, which means that we can quadratically reduce the complexity of attention without degrading performance through our method, compared to many previously existing ones that would give you gaps of even 10 points. We also evaluated this method on decoder language models of a larger size, like Mistral 7B, both in a zero-shot and a few-shot setting. In the few-shot setting, after generating the vocabulary and the corresponding embeddings with the HyperNet, we would further fine-tune it based on in-domain examples for the target language. And in the setting where Mistral was evaluated, we focused on transfer to tokenizers that, for instance, are optimized for certain programming languages. So you can see on the bottom right results for JavaScript, Go, Python, C++, and Java. So for those, again, we substantially increased the performance compared to previous method, matching the original one in the few-shot setting. There are a few cool findings that came out of this. Basically, one cool finding was that this method is very general, because even if there exist different families of tokenizers, think Unigram versus BPE versus others, we can transform any of these families into a Unigram tokenizer through a process we call unigramification. Another cool finding was that you can do this process just once per family of models, because once you generate the embeddings for the base model, they work fine also with their fine-tuned or post-trained counterparts. So you don't need to retrain your HyperNet for every copy of a model, you just need to train it once for a high-level family of models like Mistral 7B and all its variants. We also tried to push this to the limit, trying to see how the model would perform when we want to generate embeddings for vocabularies that are completely out of distribution. And the most extreme case here is word level tokenization, where you don't segment words into subwords, but you just consider each word an independent symbol in your vocabulary, which means that now your vocabulary is hundreds of thousands of items. And in this case, we show that we can substantially reduce the sequence length, again, gaining in efficiency while degrading the performance only marginally compared to previous methods like focus that would drop by 20 points. So basically, this gives you a way to, on the fly, decide which vocabulary you wish to use for any specific downstream application and plug the corresponding embeddings into your model with minimal overhead, minimal degradation in performance. However, I want to move to an even more drastic solution. So we saw that tokenizers are bad in many ways, and one solution is to learn how to swap them on the fly with other tokenizers. Another solution is getting rid of them entirely. Can we find a way to use language models that do not operate on subwords or any other segmentations, but provided by an external tool like a tokenizer, but rather learn from bytes and then end-to-end learn how to compress information internally, so that you would think of this as a generalization of tokenization, where everything is learned end-to-end. You can compress information at multiple levels, so not just once an input and preserve that granularity throughout the entire model, but rather compress it or uncompress it according to the model itself at different layers. So you can think of this as a sort of hierarchical tokenization, but also more expressive, because most tokenization methods just assume that you want to split a word into subwords. But now with this way, you can merge information across words as well. So it is a more general and hierarchical generalization of tokenization, if you want to think it that way. So how do we do that? In practice, we want to jointly model language and learn to tokenize it and segment it. So to do that, we augment the architecture of existing language models with a neural boundary predictor. And this is the resulting architecture. Starting from the left, you have a sequence of bytes that you pass to a first block of transformer layers. Those are passed into boundary predictor that tells you where the boundaries lie to separate different groups of tokens of arbitrary length. And then in intermediate layers, you pull together representations of tokens according to the output of the boundary predictor, which results in a compression of the original sequence into a shorter one. You use internal transformer layers to process information at this coarser granularity, and then at the very end, since we're dealing with autoregressive language models, we re-upsample back to the original granularity to decode the next token. What is the effect of this? Well, on the one hand, you learn to compress information in a way that simulates abstractions that humans would do over strings. So it is, I think, cognitively interesting, but obviously the advantage in terms of performance and efficiency comes from the fact that now you can efficiently code information using arbitrary arbitrary lengths for sequences, and this reduces the complexity of the internal transformer layers, again, by a quadratic factor. You might see in this image that we add some special null tokens in the compressed representations, so they appear both after pooling and during upsampling. Those are inserted in such a way as to prevent the information coming from the future tokens leaking into past tokens. So it is a way to preserve the autoregressive property of the model during training. So what are the results here? We measured both the perplexity of the language model, so its language modeling performance, and the corresponding time and space efficiency for different strategies to learn this boundary predictor. So at least 3 strategies are the most important ones. One strategy is very naive, which is let's segment the sequence at fixed steps. So every 2 original tokens, I place a boundary, for instance, or every 3 tokens. And by the way, that automatically determines the compression rate of the sequence, which is the ratio of the length of the sequence in input to the length of the sequence after pooling, so in intermediate layers. However, we can be clever about it. We can actually learn this neural boundary detector, and we can use other ways to learn this end-to-end, which is the method you see here as dynamic gumbel, because we use gumbel sigmoid as a way to estimate the gradient of this discrete decision of whether you want to compress or not, or use external tools as guidance, so a unigram tokenizer as a way to train the boundary predictor. So maybe you would ask, why can't you use the unigram tokenizer directly? And that's because tokenizers are not autoregressive. They operate on entire sequences and break them up. But here we're dealing with a setting where we're fed information byte by byte, and we have to make decisions on when we want to compress them into pooled representations or when we want to continue with the sequence. So anyway, we can compare these 3 methods in 4 languages, which is English in the top left, Hebrew on the top right, Finnish in the bottom left, and Vietnamese in the bottom right. These languages were chosen because they represent a variety of different morphological types, which have a direct effect on the average word length. So they would be pretty much, fusional languages, languages that use a pattern of consonants using vowels for inflection, like Hebrew, languages like Finnish or even Turkish that are agglutinative, so they have a lot of morphemes that are attached to the word that correspond to different grammatical properties of the word. And finally, we have Vietnamese, which is an isolating language with very little morphology and high segmentation among words. So anyway, the story here is that if you look at the results, obviously fixed naive segmentation doesn't work, because as you increase the compression ratio, which is given by the shortening factor, the bits per character, which is a measure of the language modeling ability, where the lower the better, and I want to emphasize this, immediately grows. So as you increase the level of compression, then the performance of the model degrades with fixed compression. If you use learned arbitrary length compression, either through Gamble sigmoid end-to-end or through the supervision of external tools like dynamic ingram, you find that instead, in some languages like Vietnamese and to some extent also English, you might even improve the performance while increasing your efficiency, which is counterintuitive, but in a sense, this method is kind of fascinating because you get the best of both worlds. And if you look at the plot on the right, there we're showing the gains in terms of shortening factor again, the ratio between the original length and the shortened one, in terms of GPU memory usage, and in terms of training step time, which means that you can retain performance but have more steps per second, which means that in practice, if you match the training time, training with dynamic token pooling gives you a better performance in the end, because you can train for more steps in a scenario like pre-training where you assume you have infinite data points. And even in terms of scaling laws, if we increase the depth of our model, we see that the gap between dynamic pooling and fixed pooling, where fixed pooling at 1 is basically just a vanilla transformer, has consistent gaps between them, which means that when we scale up the size of the model, the gains coming from dynamic token pooling remain consistent. And obviously, you can generalize this method to other modalities. An example I'll give you here is speech, where given a waveform, you could either do fixed segmentation and pooling, which is very suboptimal because obviously it doesn't respect the information contained in the sequence, or you could use external methods like MFA to segment it, which would be the equivalent of using a tokenizer, or you can learn end-to-end how to segment it through Gamble sigmoid, which is what I show on the right. And in practice, what you find is that dynamic token pooling with Gamble sigmoid, which is the last group of rows in this table, actually gets you a valid test and tested performance, which is better than the original model with a level of compression at 2. So twice as efficient, but better performance. Again, these are word error rates, so the lower the better. And again, in terms of efficiency, if you compare this baseline with fixed pooling, external pools like MFA and Gamble sigmoid, where we learn the segmentation end-to-end, you can clearly see that both in terms of memory usage and compute time, we have a huge advantage over the original model. To conclude this part, zero-shot tokenizer transfer gives you a way to generate embeddings for new tokenizers and vocabularies in a way that is both efficient and retains the original model performance. But you can even push this further, and instead of learning a way to swap your tokenizers on the fly, you can find a way to get rid of tokenizers entirely by training the model or retrofitting an existing one in such a way that it learns to internally merge representations, so potentially having different sequence lengths at different layers. Let's move on to the second part of the talk, which has to do with memory. We saw already that this fixed granularity given by tokenization and the fact that memory grows linearly in transformers are connected. Basically, the number of key and value representations you will append to your memory in transformers depends on the original tokenization. So having a more efficient tokenization on the one hand would reduce the memory size. But can we go even further and find a way to compress the memory in such a way that it then lies in between the two main existing architectures? It wouldn't grow linearly as transformers, it wouldn't be constant as SSMs, instead it would be in between. It would grow sublinearly in a way that you never exhaust the VRAM memory and you wouldn't exhaust capacity, so you can incorporate information from very, very long sequences without having any sort of forgetting. So just to give you a reminder again of how a vanilla transformer works, the reason why it grows linearly is that you automatically append every key and value to your cache. This is not just a matter of efficiency. Again, we've seen again and again in this talk that efficiency and performance are kind of strongly connected. There's also a very famous phenomenon where you have a failure mode of transformers, where because of the fact that this memory is growing linearly, you lose information in the middle, which means that the transformer loses the ability to retrieve information that it found in between the start and the end of the sequence because the granularity of the sequence is too fine. On the other hand, we've seen that space-based models have a constant memory, which you can think of it as the dimensionality of the projections. However, this again has consequences for performance. Because of the limited capacity, it will end up forgetting information that is very far into the sequence. So if you look at, for instance, very common benchmarks for long context modeling like needle in a haystack, you will find that SSMs severely underperform efficient transformers when dealing with this problem of retrieving a needle, so some information, from a haystack, which is a very long sequence full of confounders. So how do we find a way to start from transformers which perform very well but are inefficient and increase their memory efficiency? There are a lot of different ways. I'm showing you this table from paper from Fu 2024 that summarizes a lot of these methods, but in a nutshell, they can be grouped into the following strategies. One strategy is quantization, basically reducing the precision of the items stored in your KV cache. Another strategy is layer pruning, so pruning some of the layers of the model, which means that obviously the KV cache for those is not required anymore. You can also be more fine-grained. You can prune certain heads within attention mechanisms to make the model leaner in terms of memory. But what I think is really promising is the approach based on token pruning or merging, because in this case it is not bounded. For quantization, for instance, you can only reduce your amount of information up to a certain point. You can reduce full precision to 1 bit, but not beyond that, right? You can prune your heads, but you have a fixed amount of heads in your model, after which you immediately start degrading performance. Compressing tokens is much more expressive, so you can achieve almost unbounded levels of compression without necessarily paying the price of degrading performance. So to give you an example of methods that were very popular for this specific family of memory sparsification, that is H2O. This stands for heavy hitter oracles. It's a paper from Zhang and others. What is the idea here? It's extremely simple. You can track the sum of the attention scores assigned by the attention to each token over time, and for every new token, you remove the item from your KV cache that has the lowest sum of scores from the past. That is a simple heuristic that is very easy to implement. It's training free, so you don't even need to fine-tune your model to use it. But obviously you have to pay a price for this, which is performance is severely degraded when compression rates are high. And by high, I mean, for instance, 4 times the original size of the memory. So we tried to come up with a solution that would provide us with sublinear memory growth, similar to H2O, but also preserving performance. And the solution we found is dynamic compression and not sparsification of transformer memory. This idea is quite simple at an abstract level, implementation-wise not much so, but what we're trying to do here is, again, to learn to segment the sequence of keys and values in a way that is autoregressive, so in a way that we can segment it during generation for LLMs, and define a function to pull each segment into a single representation. This sounds very familiar, right? It's pretty much the counterpart of what we were doing with dynamic token pooling applied to hidden representations, but applied to items in the KV cache. And now we can think of this process as a generalization of regular transformers. In regular transformers, for each time step, you have only one action, which is what we call append. Take the current keys and values, attach them to the top of your cache. Now with this variant, you have 2 possible actions that the model has to learn to decide between. One is again append. You can just decide to create a new entry in your memory with the current keys and values. The other is accumulate, which is pool the current representation, keys and values, with the top of the stack of your memory. This means that we can achieve a sublinear growth by deciding when to accumulate or merge, or on the other hand, append an item to the cache. So what is the experimental setup here? Instead of training from scratch, we retrofit existing LLMs, such as Llama 2 of different scales, like 7B, 13B, 70B, because we want to show the behavior of this method at a scale where it can be applied to state-of-the-art methods. Well, Llama 2 is not state-of-the-art anymore because this is coming from summer of last year, but you can pretty much imagine that you can apply the very same to more recent models like DeepSeek and Qwen. Most importantly, this process of retrofitting existing models only requires a negligible percentage of the original pre-training data, so it's very sample efficient, and doesn't require extra parameters. What we're doing here is making these decisions on whether we want to append or merge end-to-end based on a cross-entropy loss, and encourage the model to match a global compression rate at convergence, which means that we can control how much the model compresses information. And this defines obviously Pareto frontier, where you have different relationships between more efficiency, so higher compression rate, and corresponding performance. So what I described before was the behavior at inference time. So for each new token, you decide if you want to append or accumulate the keys and values. During training time, we want to make this process parallelizable, which is again the key of transformers. To do that, basically, we have to make the following changes. In order to simulate inference time during training time while parallelizing computation, we store all intermediate keys and values in the memory. So now the memory is not really compressed. It's just showing all the intermediate states across the process of accumulating keys and value representations. We use a mask to regulate query interactions, again, in such a way that they would correspond to what the model can actually observe at inference time. We have to relax these decisions that are discrete in nature about whether to accumulate or append into continuous ones, resulting into entangled states where you have partially accumulated, partially appended items in your training simulation of the KV cache. And we have a mask that is dependent on these decisions. So if you consider this variable alpha, which takes a value of 0 or 1, depending on whether we want to accumulate or append, and this value is discrete at inference time, but continues between 0 and 1 at training time, then this very value will regulate to what extent a certain query can attend on a certain key, which is on the columns. And besides the usual autoregressive causal mask that prevents future tokens from being observed from previous tokens, you also have this DMC mask, which again stands for dynamic memory compression, where basically we make sure that as alpha becomes discretized, this log of 1 minus alpha eventually becomes either 0 or minus infinity, which is basically what we would see at inference time. So in terms of downstream performance, what does it look like? Again, we have three models here, or better, three different scales. Blue is 7B, green is 13B, and red is 70B, so different sizes. You also have different levels of compression. So here we're showing 2x and 4x, and different downstream evaluations. On the left, you can see that different plots correspond to MLU, which is a factuality benchmark with multiple possible answers for a question about a subject, which could be, for instance, law or math or science or literature. On the bottom, you have human eval, which is a benchmark that is about mapping text to code. So given a textual description, generate the code that implements that description. And now you can see that using DMC, which is the continuous lines, as opposed to broken lines, which represent GQA, which is at the time of this paper the strongest baseline for memory compression, not only you have much better performance, sometimes even surpassing the performance of the original model, surprisingly, but also much higher sample efficiency. So for instance, to reach the level of performance that you have at iteration 8,000 for dynamic memory compression, you need to go all the way to iteration 20,000, for instance, for 13B. So more than twice as many training steps. So on the right, you can see more specifically the performance of these models. One is MLU based, and so again, that is a factuality benchmark, where you can see that for DMC at different levels of compression, we are pretty much around the original performance of 44.6. But for human eval, we often surpass the performance even at high level of compression. So we start from 14.0, and for DMC 4x, we reach 16.5, which is again kind of surprising. Similar for 13B, where we start from 17.5 and reach 22 with a compression of 4. And that has multiple possible explanations. Most likely it doesn't come from the extra training, because it corresponds to basically 1% of the full data observed during pre-training, but probably leads to more efficient and better encoding of the information related to text and code, which in turn results in better performance. We also show at the very bottom that DMC is also, in a sense, orthogonal to existing methods like GQA, because you can compound them. So if you start from a model with GQA 8x and apply DMC 2x, that gives you a compression of 16x, and still that doesn't degrade performance compared to the original model in either of these benchmarks. There's also a further column, which is CSQA, which is basically question answering based on common sense, which shows patterns very similar to MLU, so I won't discuss it in detail. I also want to showcase the results that have to do with the efficiency of the model, and specifically the throughput. So you can see here the comparison between the vanilla model to the original transformer for Llama 2 and the DMC variants with different levels of compression that correspond to different colors. You can see across the rows that each row corresponds to a specific GPU, so A100 and H100, and we report the number of tokens generated per second, which again is a measure of throughput of the model. For the batch size, that is the largest batch size that doesn't run out of memory for that specific model. So on the one hand, you can see that basically moving from the vanilla model that takes at most 16 examples, you can move to 128 examples in a single batch. And not only that, if you consider this, you can increase the throughput 7x on an H100, which means that you can speed up your model 7-fold, which is kind of impressive gain, again, without renouncing to performance. There's also an interesting pattern if you consider not just the throughput, but also the latency, where basically the latency is just the time it takes to start the generation. And this is kind of a two-part function, right? So in the first part, the line is almost flat. So basically you can increase throughput without substantially changing the latency compared to the original model. But at some point, you start increasing the latency when you have a much higher throughput, which again corresponds to pretty much corresponding levels of compression rate. So for throughput of 7x, you can imagine that here we're dealing with a compression rate of 7x. This is because up to a certain threshold, the model is memory bound. It means that for computing attention, it is more compute intensive to retrieve information from memory than doing the actual computation. But after a certain compression rate, it becomes compute bound. So now the memory is smaller because we have a much smaller KV cache, and so retrieving it is more efficient. But then now the cost of computing becomes more prevalent if you compare them. And so at that point, you have this transition where you start paying some price in terms of latency. So anyway, we can also visualize this process of compression. So we can see how the model chooses to compress information, comparing its behavior across different layers, so at different points in the depth of the model, and different heads, so different components of the attention mechanism in each layer. And I think you can see a very clear pattern on the right, which again shows these four different model sizes and different levels of compression. And the pattern is that, interestingly, the model decides to compress the most in the second part of the model. So in the second part of the model, you can reach levels of compression up to 14x for a lot of heads, which are shown on the y-axis. But for the earlier layers, which you can see on the x-axis, instead the compression is much smaller. So the model is matching this global budget in terms of compression, and it's deciding that information in the earlier layers is much more valuable and less compressible than the information found in later layers, which I think is also interesting from sort of interpretation of the model and its behavior. So let me get to the conclusions. We showed here that merging is superior to sparsification for memory compression, which means that compared to all previous training-free methods that just delete items from the cache, we can achieve a strategy that both preserves performance and yields very, very high levels of compression, which results in higher efficiency. And this idea of retrofitting is also very promising because it constitutes a good compromise between training-free methods that are cheap but degrade performance and training from scratch, which is obviously impossible with this scale of models, because retrofitting only requires, again, a very negligible amount of examples to basically transform the architecture of existing models into a new one. So for future work, I think it might be interesting to explore more expressive strategies for compression that, for instance, are capable of hierarchical or discontinuous compression that merges items that are not necessarily contiguous in the sequence. Making Markovian assumptions over the compression, so making compression time dependent. At the moment, compression is time independent. Different positions in your sequence will be pretty much on average compressed the same, but you can make an assumption that, for instance, recent information is compressed the least because it is the most relevant, and compressed information in very far away points in the sequence should be higher. So we will try to see if this kind of biases actually helps, and obviously we will see how applying these ideas connected to memory compression might actually benefit long context tasks, for instance, prevent lost in the middle phenomena and limited capacity issues, as well as trying to see how this works in long generation. So the conclusions about the question that we started from, which was, can we adapt the granularity of memory and tokenization for conditional computation, are yes, we can achieve that. In particular, we should probably get rid of fixed tokenizers, either by having a tokenizer that can be swapped in and out on the fly, or models that operate on bytes and learn end-to-end how to compress information. So these were the two projects I presented in the first part. In particular, tokenizers can be transferred zero-shot to encode sequences more efficiently, and also enable merging and mixing of the logits of different models with different tokenizers. We also saw that tokenizers can be learned jointly with the language model to process text at different granularities and learn these abstractions from raw data. Also, the second group of main takeaways is that memory in both transformers and state space models, which again lie at the two opposites of the spectrum between linear growth and constant size, both of them actually may lead to information loss. So if we can find a way, such as through dynamic memory compression, to grow the memory cell linearly and adaptively based on the input sequence, then we can find a way to neither run out of VRAM nor forget past information because of limited capacity. If you want to know more, actually, I gave a tutorial with Andre Martins at NeurIPS last year in 2024. We have a website here where you can find a lot of notebooks and notes about a lot of these topics. and more. So feel free to take a look if you are curious about these research directions. So having said that, many thanks again, and very happy to answer any of your questions.